So our next speaker is Josh Portlock. He's the founder and chairman of Electro.Aero. Josh is an Australian innovation leader in commercial drones and sustainable aviation. He founded ScientificAerospace to further develop and commercialize his electric ducted fan VTOL drone technology. The company has been trading for over a decade and is now growing through mergers and acquisition with focus on spatial accuracy, spectral fidelity, and end-to-end aerial data solutions. Josh founded Electro.Aero in 2014 with a vision of safely propelling sustainable aviation. At the beginning of this year, Electro.Aero was the first to get a Pipistrel Alpha Electro certified to provide paid recreational pilot training, helping pave the way for other countries and manufacturers. Electro.Aero is also the Asia-Pacific distributor for Sunflyer 2 and 4. Josh works closely with partner company Trek Aerospace on a variety of electric aircraft projects, including their FlyKart 2, which recently won the top 10 GoFly Phase 1 design competition. Josh's title is Building Blocks for Sustainable Aviation, Electrofans, and Universal Charging. Please welcome Josh.
Well, thanks for having me, and thanks Yelena and all the organizers for holding this great event every year and putting the effort in. Much appreciated. And Paul and I have come a long way, 32 hours of travel, 4 flights later. I think I'm barely on the right time zone, so hopefully I'll keep with you here. So we're going to go over the background of Electro a little and what we're focusing on there. Trek as one of our key partners here in the US, and the FlyKart 2 is a bit of a fun project. But really what I've learned over the last 4 years of getting involved in this space, but particularly 6 months with operating the Alpha Electro, is there's still a lot of improvements can be made in the building blocks to make this a really compelling industry. And I've sort of learned from the last decade of drones that you can do things better than trying to do everything yourself, and collaboration is definitely going to help us as a group rather than sort of secretive competition. So that's my push, is to get things more collaborative, and we feel we can contribute in the propulsive side and the charging side and work with others on everything in between.
Electro.Aero was founded by Australian innovator Joshua Portlock with the vision of safely propelling sustainable aviation. Beyond the environmental benefits, electricity and maintenance of electric aircraft cost significantly less than petrol and engine overhauls, making flying sustainably more affordable. Electro.Aero have partnered with Pipistrel, an award-winning light aircraft manufacturer, to represent the Alpha Electro in Australia and facilitate affordable training for new recreational pilots. For commercial pilot training, Electro.Aero is the exclusive distributor in the Asia Pacific for Sunflyer from Trek Aerospace. The Sunflyer is aiming to be the first FAA-certified electric aircraft with a proposed flight endurance over 3 hours, assisted by solar panels on its wings. Electro.Aero has invested in Trek Aerospace, the world leader in efficient ducted fan optimization. Together, they developed FlyKart, a personal flying go-kart concept that can be transported on a trailer and employs redundant fly-by-wire systems for safety. They are also developing a line of integrated electric ducted fans called Electroducts. These will support a wide variety of VTOL and other aircraft manufacturers who desire safe, compact, and efficient propulsion systems. The long-term mission of Electro.Aero is to commercialize fleets of electric air taxis to fly passengers quickly and affordably over city traffic and water. For this reason, Electro.Aero has developed an automated booking system at Rottnest.Aero for the existing Rottnest Island air taxi services. This collaboration has further proven the need for electric passenger aircraft.
So yeah, the focus has been on both ends of the spectrum. So operating the latest state-of-the-art aircraft and helping distribute those in our region and really paving the way, particularly our relationship with CASA and leveraging that. And then the other side is helping the industry with modules of components and technology where we have some expertise. So this is pretty exciting activity. Started this year. We got our first Alpha Electro certified. And the curious backstory is that we actually beat Pipistrel to it, even in EASA, and certainly the FAA is still trying to work out how to take out reciprocating engines from their light sport regulations. So we want credit to CASA and the fact that we have a long-standing relationship, and Paul Dwyer, our regulatory manager, has worked with CASA on the drone space for the last decade and helping pioneer that. So we had a really good, I guess, relationship with them to have that conversation. And it took a while, it took about 1.5 years, to be honest, from when I first started a conversation with CASA and said, hey, I've ordered an electric aircraft, can we certify it? To, hey, it's coming next month, can we get this paperwork done? To, it's here now, we're going to go fly it, is that okay? And they were surprisingly pretty receptive to that. And they said, yep, if you do a check flight and it's designed and manufactured to ASTM standards, then yes, you can operate that commercially and start charging money. And I think the reality check to a lot of people in the industry was like jaw-dropping, what? CASA have done this before FAA and EASA and others? And yeah, I think it's sort of testament to our relationship with them and that they're a bit more receptive to industry-driven regulations. So we are lucky in that regard. We can sort of write the rules, ask for permission, and they'll say, yeah, that's better than us writing it. So it's almost a bit of an easier process than necessarily waiting for regulations to write the new rules. But yeah, so we are wanting to, the next step is with George and getting the Sunfire certified when it's ready. And we feel that's a really exciting opportunity to continue leading the way in airframes. This is a bit of a sales pitch video, but we'll play it anyway. It's more for getting people excited about coming and flying electric. You guys are already there, so it's not for this audience. But if I play it for the sake of showing what we're trying to do with promoting this industry.
Experience the world's first electric plane available to the public. And if you're feeling adventurous, you can even take the controls.
Amazing. The views are incredible. The plane is really quiet. I think it's really cool that it's an electric plane. Like, I highly recommend it. It's one of the best experiences I've had.
Book now at Electro.Aero.
So if you ever want to come down to Perth, Western Australia, it's only 32 hours away at the moment to fly. So it's a bit of a long trip for you to come, but do try and make it and visit us in Perth if you can. So a bit of exciting things we've tried with it. You know, we pushed the envelope a little for this little alpha. We wanted to do our first cross-country. Now, obviously not across the entire country, but we wanted to demonstrate that it could fly more than the 25 nautical miles of a typical light sport aircraft. And there we went to a regional airfield to demonstrate that you'd have to actually do, you know, navigation and plan for fuel reserves and whatnot. So ironically, you know, this super lightweight little 380 kilo electric aircraft needed a 400 kilo genset to recharge it in the field. And even then, that genset in the 40-degree heat of Australia was struggling and like tripping out from the charger, so we had to dial down the charger and things like this. So it goes to show the technology density that's gone into electric aviation versus legacy power systems. It does put a question on hybrids being viable, in my opinion, because if that's a 20 kilowatt genset that struggles, it's going to be quite challenging to get that sort of power density out of hybrids and carry it on board the aircraft. But look, lots of lessons learned from that, and we really learned particularly about charging infrastructure being a huge need in the future, and I'll talk about that later. Trek Aerospace, I feel, is a really valuable add to this industry, and they were really the pioneers of VTOL personal flight. I'm not sure if you're aware of this, but Rob Balaga was the first to fly a powered lift aircraft over 20 years ago now, and they won a $5 million contract to develop the springtail. And really, they led the way. They were innovators, but they were encumbered by engines. They had these noisy rotary engines fanging behind them, running through really complex gearboxes and drive shafts, and that was what let them down. The reliability and safety of engines and noise and harshness really meant that it wasn't a viable product back then. So, fast forward 10, 15 years, electric started to be more dense enough to propel electric fans. The ducts now make a lot more sense again. You don't have to deal with gearboxes and engines and all that complexity. You can have a direct drive motor right in the middle. Then you start to really benefit from the aerodynamic efficiencies of ducted fans. Because if you've got a big engine in the middle of your quite compact duct, you're not efficiently propelling air through it. If you've got a little electric motor in the middle and it's all optimized for the flow, you can really see the benefits again. So as a bit of a proof of concept, Rob and I built FlyKart a 3-month rapid prototyping project, 3 months before 2016's CAFE, in fact. We said, you know, let's just build something to prove we can fly vertically with ducted fans and make it as compact and kind of cool as possible. So the design requirement was fit on a trailer, you know, in any garage and mobile from the roads, yet carry a person and fly around. So we did this as a proof of concept. So I think it was about February we started designing it, and we had it flying by May before CAFE 2 years ago. And really what that did was actually, we were thinking, oh, I wonder if there'll be a big business out of this, selling personal aircraft. We were just sort of testing the market. But what did come out of it is people go, whoa, really? You're achieving that much propulsion power in that small footprint and you're converting electricity to thrust that efficiently? It's like, yeah, that's what these ducted fans can do. So we've been selling our ducted fans this size and bigger to a variety of companies, a lot that we can't talk about, but some we can, like great partnerships with Aerospace on the TriFan project that we're supporting. And we're really trying to help industry adopt ducted propulsion as a part of the Electra ecosystem. This demonstrates the fault tolerance of an octocopter. It's no real news to most people, but it does show that the stability is just as good with 7. The only noticeable difference is that you can hear the 2 fans next to that turned off fan working a little harder because it's having to compensate and trim. But from a remote piloting point of view, I couldn't tell. So then along came GoFly. So GoFly announced a few months ago now that they were starting this prize, and I thought, oh, a good opportunity to dust off FlyKart and do it even better. So we basically designed FlyKart 2 around the design criteria of GoFly. If you're not familiar, it's a Boeing-sponsored $2 million prize pool to design and manufacture a prototype of a personal flight aircraft that could fly 20 miles as fast as possible, but that's not the most important thing. It's as compact and as quiet as possible. And Rob and I are like, well, that's what ducted fans do, so let's enter this. So in the design optimization, we had to fit in the smallest space, but it's a very complicated, multi-dimensional design space, because if you're trying to optimize for noise, you don't want to have too high a disk loading. You want to have a lower disk loading, so in theory, really big ducts running less airspeed through them, and yet you get points for compactness. So there's a real little push and tug, pull and push on the requirements there. But we ended up just adding 2 more ducts, and that was around the sweet spot for noise versus compactness. And still quite a comfy little armchair. People have called it the flying deck chair. And I guess the funny thing is watching the media results from this, right? Because the top 10 designs were all published on the web. And I was quite proud that we were there was a chart for most likely to kill someone. We were on the lowest. So that was nice. We were like the least likely to kill someone. And then all the others were like, had a little catchphrase like Death Trap 2000 with all the open rotors or like really exposed cabins and whatnot. So at least we were, on the safest of them in the list. And it is interesting to see public perception on this, because in some sense everyone wants personal flight, right? But there's a lot of pushback about the exposed cabins or the exposed blades and things like this. We don't necessarily see this being a short-term commercially viable product, so I'm not saying that we're trying to get this to market, but it's a fantastic education platform and a discussion point for what could be a reality one day. I'm personally more interested in enclosed cabins and a more comfortable and safer environment, but it does kind of keep the excitement going with electric aviation and VTOL and personal flight. Yeah, another viewpoint for you. We sort of went over the top on the CG to really wow people. So what I really want to talk about and share with this community is the building blocks of sustainable aviation. And I've sort of broke it down into these 5. Admittedly, 3 of them are sort of collectively talking about charging, but it's actually a huge factor, and I want to emphasize that. We're helping on the propulsion side. We're really focusing on those ducted fan optimizations, tightly integrating electric motors and speed controllers. But we're not necessarily focusing as much on batteries. We want to let the giants focus on the cell level. Let the Panasonics, LG Chems, and Sony spend their billions of dollars in the cell optimization, and Teslas on manufacturing. And then really partnering with leaders in integration of the actual batteries as far as safe housings and whatnot. But where I can add some value and share with you is that we've really identified a need for modular propulsion. And if you look at the way aviation has progressed over the century, it's really accelerated when you separate airframers and propulsors. So if you think about the big names of the aviation industry, starting at the top, you've got the Boeings and Airbuses as airframers, and they have the Rolls-Royce, the GEs, and the propulsors as separate partners, right? So, and that's because they do that really well, and Boeing do and Airbus do their airframes really well. So it gives some focus on what your value add is to the industry and ecosystem. The same can be said from the bottom end up about Rotax, 80% market share in light sport, and Lycoming having a fairly large market share in the Cessna and sort of general aviation. So we sort of see ourselves more as the Rotax of the sustainable aviation industry, rather than trying to build aircraft entirely from scratch. And as Kevin was saying, that you don't really want to be trying to do everything from scratch in a closed box, because there's lots of other people out there doing it better, and if you collaborate you can actually value add a lot more, and we can get to these ambitious target goals much sooner. So a bit of a technology discussion here about why ducted over open prop, and this top one on the top right really emphasizes that the flight speeds that electric aviation is likely to be flying in the foreseeable future is sub 200 knots, and that's where our optimized ducted fans work quite nicely. So basically from zero, from a static hover point of view or thrust, you've got about a 40% excess thrust for the same power, and if you flip that around the other way, for the same takeoff thrust, you're using about 30% less power, or effectively 40% more endurance. And the nice thing is it actually is a hump in it, where during climb and a slower speed flights, like an ultralight class, we're getting closer to 50%. So then in a slow speed cruise, like an efficient L over D cruise, you're actually getting close to 50% more endurance out of the same battery size. And that's a real technology enabler. That's taking something like our Alpha from an hour endurance to an hour and a half, and other aircraft in that sort of 50% more range out of the same battery. And the other way to flip it around is if you want a certain amount of range, that's now a 30% lighter, cheaper battery. Like, that's a big deal from not just upfront cost and weight penalty, but your ongoing cost of replacing that battery and charging it every time. Half as loud is a good just general metric, and the only way we achieve that noise reduction is through really careful tolerance manufacturing. So our real IP and value add collectively with Trek is manufacturing these ducts to be as light, as circular, and as perfectly round and concentric as possible, to get that tip clearance as small as possible. And I'm not going to tell you how we do that. But it is important, it's extremely important. You have too much tip clearance, you may as well not have a duct. So the cruise benefits are also quite important, and this only shows, I need to change this actually, because this only shows the sort of FlyKart benefit of tilting forward. So as you tilt forward into the forward flight direction, the ducts produce extra lift. The leading edge of the duct is like a blown airfoil, because you're sucking air over the top and blowing it over the back. You're enforcing the attachment of the front half of the duct. But this only tells half the story, because that's tilting at about up to 30, 35 degrees, so you're sort of flying forward at an angle. But if you then optimize an airframe to fully transition, like the Trifan, to have horizontal flight ducts, then you've got an even further reduction in drag by having an actual attachment of the flow over the ducts, and you're getting high-speed cruise, like a lot of these transitioning aircraft can achieve. The thing that I'll emphasize here is that you're not really having to compromise your propulsor too much to do both hover and high-speed cruise, because you've got a higher disk loading by nature of a more compact duct. So in reasonably speed cruise, your same fixed pitch prop, it works quite efficiently, around 85% figure of merit in hover and around 80% cruise efficiency. So as opposed to an open prop, if you've started off in a hover and then you've transitioned with a fixed pitch prop, you're definitely going to trade off one or the other substantially. You're going to be back around the sort of 50 less percent in hover or 50 less percent in cruise. And that's a really big factor. It sort of further compounds the benefit of ducts in these VTOL transitioning aircraft. Explaining the endurance trade-off with ducts, and this is kind of across the board with electric propulsion. You really want to get out of this like high power region, right, where you're using a lot of power and in hover, so you want to get to that forward cruise speed where you're reducing power substantially, and that's where your endurance numbers can stack up substantially. This is only showing a very minimal battery size, so this is whether it's a hybrid system or a different combination of energy cells and power cells. This is just the worst case batteries we could actually integrate into the ducts. And I have a provisional patent on battery integrated ducts. So it gives you a modular power system integrated into the duct itself, and then you add your high energy cells in the fuselage for longer flight times, or hybrid if you really want to waste your time on that in the short term. So it really depends on the mission profile, I should clarify. So the mission profile, if it's highly endurance focused, then you may tinker with hybrid. And if you have a big enough aircraft to justify an efficient conversion system, then you go hybrid. But for the small aircraft, I'd highly recommend not doing it and focusing on just furthering the electrics. Gyrocopters are a funny aircraft, not that popular here, very popular in Europe, and because of their versatility of fitting, in a garage for private ownership and being able to take off and land in relatively short areas. But by nature, they're quite power hungry, so they are about a 4-to-1 L/D compared to sort of 10-to-1 in a decent fixed wing, and that means it's really one of the less likely ones to be converted to electric because of that, higher power consumption in cruise. But with our optimal ducted fans, our 80 centimetre ones here, you can position them aerodynamically much more efficiently around a very streamlined fuselage, and you've now got a compounding effect of efficiencies because you have the propulsor being very efficient, clean air intake. You've got the airframe being a lot more efficient, lower drag without air being blown over it. You've got a lot less vibration and harshness without the engine back there. So it sort of ticks a lot of boxes. And we did some calcs on the endurance, and actually we were getting basically projections of up to 90 minutes of endurance with a 20 kilowatt hour battery. That's well within the weight limits of current battery technology, replacing the Rotax engine in the fuel tank with batteries and putting our electroducts on the back. So to get over an hour, and that's including reserve, so really it's an hour plus half an hour reserve, out of a gyrocopter is actually quite a feat. And if I should do another equivalent to a fixed wing where we're getting sort of 2+ hours endurance out of the sub 600 kilo takeoff weight. So we do feel there's a really good value proposition to collaborate with industry on the light sport category with our electroducts. One challenge we have though that I'll be open with is that twins are not very light sport friendly. So we've talked with CASA and FAA and said our twins are just as safe as a single, very low dissymmetry of yaw and all these justifications that it's one lever, but no, they just sort of say, I'm sorry, that's sort of hard written into it as a non-multi-engine for light sport. So we see this more as experimental and maybe for people who really want to experiment with the latest state-of-the-art technology. But eventually twins in larger aircraft, 4- and 5-seat passenger air taxis, does definitely make sense for that twin flexibility and redundancy. Okay, chargers and standards. It's really racked my head the last 6 months. I have been really frustrated by charging standards, and I felt I should share my not just frustrations, but suggestions on what we could do better. And we can learn a lot from the automotive industry. So if you look at what they did, and this is a little history lesson on the EVs, the electric vehicle evolution of charging standards, and this half a dozen of non-compatible mechanical, let alone the software protocols. So Chademo came out, Japanese, designer manufactured, really driven by Nissan. Fantastic in the first principle of a lot of power through two big DC connectors. And by the way, I'm not even going to talk about AC, because I don't feel AC is a viable charging standard for electric vehicles because you need a chunky AC to DC converter, which is dead weight on your aircraft. So you should always take that AC to DC conversion off your aircraft, maybe carry it in the aircraft if you're going to somewhere rural, but it shouldn't be a standard equipment, right? So just in DC, you've got Chademo, reasonably high power. They're moving from 200 kilowatts to 400 kilowatts, so you can deliver a lot of power, but I wish I brought one with me, but I would have been oversized luggage because they're really heavy, like really chunky metal connectors, take a lot of force to connect. There you go, bring it in for us. You can compare it to what I'm going to suggest. But look, and credit to them, they pioneered, they leaded the way, so they had to just do something kind of over-engineered. But then lessons learned from that is, some lessons learned were Tesla said, all right, well, we don't need all this. Let's make as compact as possible connector that just does 2 DC plugs at the highest power we're likely to need in the foreseeable future, and keep it all lightweight and compact. So credit to Tesla with their proprietary standard. It's fantastic. It's compact. It's dense. It delivers a lot of reasonable amount of power, but they've bottlenecked themselves from that original design. They've said, the most we think we'll need is 410 volts for a 400 volt battery, 330 amps, if you don't mind quite a thick and hot cable, and 135 kilowatts. Most of them are around the sort of 100 or 120 kilowatts, but the 135 is the theoretical peak. So the risk with that is you're now limiting yourself. You certainly wouldn't want to use a Tesla charger for a regional jet. You'd be on the runway all day waiting for it to be topped up. And you certainly, any high-performance aircraft as well, you wouldn't really be able to charge at the rates you'd need for a quick turnaround time. CCS is the, I don't know if I'm allowed to use the word bastard child of standards, but I'm going to say it anyway. It's kind of like a second thought of, oh, we've got this AC standard of single phase with the type 1 or 3-phase with the type 2. Let's just chuck 2 big-ass DC connectors on the bottom. I really don't like it. My personal gripe with this is that it's chunky, it's overweight, especially the reciprocal is very chunky. So on your aircraft, that's a fair bit of weight. And the method of communication is unique. It's called PLC, which is power logic conversion, I believe. Power level communication. And what that really is it's communication over the DC cables. Now, in theory, that makes sense for reduced cable cost and weight. Instead of having a couple of twisted pairs in the cable for communication, you've got the DC cables communicating. But to do that, you now need much more expense in components either side, on the aircraft side and on the charger side, which is more weight and more cost, to actually turn this communication protocol into high voltage communication over the DC cables and tolerate all the noise and everything that comes with that. So while it's worked okay and reasonably well in the automotive industry, the automotive industry doesn't have the same weight and cost sensitivities of airframes that we do, so we really have to focus on what is the least cost and weight on the aircraft to make a viable charging standard. So the lessons learned from both of those, in fact all 3 of those, including the 2 variants, just to explain for people who aren't from international, the international standard for Tesla is a combined Menekes type 2 connector, which is the same as the AC connector for CCS. So what I really don't like about it is that it's physically the same connector, but it doesn't communicate the same way, and that really trips people out if you sort of show up at a charging station, plug in, and nothing happens, or worse, something fails from being incompatible. But what they did right was that they are catering for both 3-phase and DC in the one connector. So again, credit to Tesla, they're a pioneer, so they had to sort of think differently. And they said, all right, internationally, let's make it 3-phase compatible for AC charging, but then the same plug has to take DC fast charging over the 4 pins. So instead of having neutral line 1, 2, and 3, it's got 2 positives and 2 negatives, and that way you can get reasonably high, I think it's 80 kilowatt supercharging through the same pins. So in Australia, that's our standard. But and look, you know, when you're pioneering an industry, you've got to pick something, right? And I think they picked right at the time. But then comes the GB/T standard. Now, this is a real eye-opener. When I started to see these statistics, I was like, whoa. So you've got the benefits of 2 big DC pins that all of the top row are effectively using, without the complexity of AC pins that you really don't need in the GB/T. And the adoption rate is phenomenal. So Chademo started about a decade ago, and they have around 16,500 charge stations with a Chademo connector on them. CCS was a later comer to the table. In fact, I'll say Tesla was next, and over the last less than a decade, they've had about 10,000 charging stations. CCS was a little bit of a lagger in adoption, but it was really the general public version of what Tesla were trying to do, and about 7,000 charging stations. So I was going to plot these, but I didn't have enough data to really show you this. But if you look at the sort of linear growth rates of building charge stations, GB/T only came out in 2015. So in less than 3 years, they have over 127,000 charge stations with this connector on it, right? And this connector, the GB/T, is the best of all worlds in the sense that it's a high-powered 200 kilowatt DC pin with a proper differential pair CAN bus that communicates very simply between CAN bus devices either side of the charge cable. You're not trying to use complicated high voltage level PLC-based communications. And it takes SAE standards as well, so they've adopted international standards for communication, so that they're not trying to reinvent the wheel with communication standards. The pins are not too dissimilar to the CCS pins, they just happen to be more tightly integrated into one standard DC-only plug. Now, in China, which was, and this was the real, I think, nail in the coffin, in my opinion, for trying to do anything else other than GB/T, China has heavily subsidized the cost of these charge cables and connectors because they pushed this standard. And they pushed so hard that you're not allowed to sell an electric car in China unless you go with this connector. So even Tesla is actually catering for this connector on the Teslas in China, right? And to me, if you can move a giant like Tesla to a new standard, you've got something going for you. Now, I've looked further into it about cost and value. You're talking about like high hundreds of dollars, if not over $1,000 for the 400 kilowatt version of that charger. You've got CCS is in the middle hundreds of dollars, in the $500-600. You can't even buy a Tesla charger unless you've got a Tesla and you're using it legitimately for a Tesla, but you can buy a Menekes Type 2. Now, this is what Pipistrel used, just for everyone's reference. It's a Menekes Type 2, but with a further third non-standard communication protocol. So you've now got at least 3 physically the same plugs in the world of electric vehicles that do not communicate with each other. And to me, that's a real misdemeanor as far as actually like confusing the public, because you're thinking, oh yeah, that looks like it'll fit and doesn't do anything, or worse, fries the electronics because it's a completely different communication protocol. So at least by changing the mechanical standard and having the same or very similar CAN bus standard to these two, so these two are CAN bus, whereas the CCS is PLC, you're at least catering for a more compatible ecosystem, where theoretically, if you've got a GBT socket on the aircraft, you could very readily make a Chademo adapter or a Tesla adapter, right? So you use the affordable sort of interface as the standard, is what I'm proposing to the industry, and then you could make affordable adapters. It's not affordable at the moment to make a CCS adapter, so that's a bit of a separate category. But what it really does emphasize is that in China, the standard now is that there's a Menekes Type 2 for 3-phase and a DC plug separately for the GB/T standard, and that way you kind of know you're either plugging in DC fast charging or AC. And on almost all aircraft, we wouldn't even have the AC socket to save weight and complexity and cost. Okay, that's my pitch, but just to give you a warning that this isn't a done deal, and obviously I've got to try and get partners in this aviation industry on board with this recommendation of GB/T. So on Monday, tomorrow morning, we're meeting with SAE and ASTM, and I'm going to be talking more with George and others about making sure we do this right. So while this is my recommendation, I'm more inclined to say, let's just go with whatever everyone agrees with and be consistent and standardize, and that's going to be the best for everyone in the industry. So there still is, the jury's not entirely out, and there is new standards coming up all the time. This is the new Chinese standard for high power, and funnily enough, it's very similar to what they have now, but they wanted to go that closer to megawatt class. So instead of being limited to, say, 200 kilowatt, which is fine for cars, light aircraft, to do buses and regional jets, you want closer to a megawatt. So by having the same CAN bus standard, the same or very similar interfaces, you're only looking at an adapter change to go to the higher power pins. This would sort of future-proof it for regional jets as well. So by going a GBT standard now at an affordable cost I forgot to say, this is only $120, by the way. So it is a very affordable connector that is really well manufactured. And I've bought several from different manufacturers now, and they're all quite high quality. So I'm at that point where the value proposition of this is just a no-brainer, but it future-proofs to upgrade to regional jet class sort of bus level charging. By the way, on that note, I think I've got a few minutes to add to this, is that if you have a pseudo-regional jet, say a 6 to 8-seater, that's maybe needing 300 to 400 kilowatts, you can simply use 2 guns. And that's how they do bus charging in China at the moment, and most places actually, is you have 2 of these guns plug into 2 plugs, and you've now got 400 kilowatts over 2 cables. And then if you happen to have 2 small aircraft show up at the same dock, you can plug them in separately. So it gives you that flexibility with just 2 plugs or 1. So that's sort of the interim fix for like thin haul regional, and then the new GBT standard, which they're pushing hard for even larger buses and things like that, where they want to do supercharging on buses in like 10-15 minutes. Then they need that sort of near megawatt class of power. But that's my recommendation. And like I said, the jury's out. The jury's not out, and I welcome industry feedback on this recommendation. And we're going to be looking at starting a group, a standards body, if you will, for electric aircraft charging standards. Still playing with the acronyms and names, but it could be something like CAFE, standing for charging standards. But CAFE are going to be involved. We're trying to get SAE on board, ASTM, Sunfire. George is going to be a really valuable partner, and obviously Ampere. So anyone else who wants to be involved, just feel free to contact me, and I'll get onto that group email that will start after tomorrow's conversation with SAE and ASTM. Thanks for your time. Any questions? Oh, no, questions after George. Okay, thank you.